Welcome to HurricaneCenterLive.com. I'm Alex Garcia, Director of the National Tropical Weather Conference and Executive Producer of these programs. These programs are made possible by USAA, the South Padre Island Convention and Tourist Bureau, and Plyloc's Hurricane Clips. These programs are also a team effort with Bill Reed, the former Director of the National Hurricane Center, and Tim Smith, Chief Meteorologist of KRGV-TV. And now, here's Tim Smith.
Thank you, Alex, and good morning, everyone. Welcome to NTWC Live, coming to you live from tropical South Padre Island, Texas today. This is a unique day because sitting out on the beach on South Padre Island, Texas, wearing a jacket because that cold front came through, and right over there's a hurricane. That's an unusual thing. We don't see that very often when we're sitting in the 50s and there's a hurricane sitting just offshore. We'll find out how far just offshore in just a couple of minutes. Bill can tell us how far away it is. But we've got a great program for you today, and we're going to get to that in a moment. But first, we want to thank our sponsors who are with us once again this year and have been all year long for NTWC Live. Of course, South Padre Island Convention and Visitors Bureau, that's where we are now. In fact, I'm at the Haus Hotel. What would have been the 2020 National Tropical Weather Conference, the Marriott Courtyard on South Padre Island. We hope to be back here in 2021. This could be your room. This might be your view if you show up for the 2021 conference. So it's a great place. The fishing pier being built back there. It's going to be 1,000 feet long by the time it's done. So a great view here on South Padre Island. I also want to thank Plyloc's Hurricane Clips. Those folks have been doing a great job all season long. I have a hunch they've sold a few this year because it's been such an active season. So thanks to Plyloc's, and also thanks to USAA, a big part of all the things we do at the Storm Science Network, and we appreciate the support of USAA, really making a difference in our community. Okay, let's find out what's going on right out there right now. Let's turn it over to the man with the plan, former director of the National Hurricane Center, Mr. Bill Reed. Good morning, Bill.
Hey, Tim. Glad to see you in a jacket. It's cool here, too. The front stalled over us for a day. It waffled back and forth right over League City all day yesterday. But this morning it shoved offshore and it's chasing Zeta, and it won't catch it before landfall, but it will be a player. So let's get right to it and talk about what's going on in the world of Zeta. Hopefully it'll come up. And start with the water vapor animation of the big picture there. Obviously, there's Zeta in the middle of the screen there, and you can start to see the eye redefining itself again. Earlier, it was clearly defined, and this morning it got kind of cloud-filled. So you got a good eye, you got very good outflow. Doesn't look like much shear around it yet, and doesn't look like dry air unless it's sneaking in underneath the cirrus level clouds. I don't see that at this time, though. The two big steering mechanisms are the large subtropical high extending into the eastern Gulf from the Atlantic, and our big winter storm has produced record snow, cold, and ice across the southern plains and southern Rockies, is now centered over southeast New Mexico and is making a steady track eastward and will be the driver on where this thing's going to go over the next several days. The visible loop in close on that, you can see the eye starting to poke through, but there's still a lot of cloud contamination, probably in the low cloud range there. You can see the leading edge of the Arctic air now coming into the outer part of the circulation of Zeta down here east of where Tim is at. And the outer rain bands are starting to come on shore, and a pretty good slug of rain will be entering Louisiana if it hasn't already done so very soon. The latest on the recon, the Air Force and the NOAA have both been out. This is just happens to be the slide from the Air Force. You can see how fast the storm is moving north. The standard alpha pattern, they're having to always adjust for the higher speed northern motion, and the pressure is still going down. They're down to 977 on their latest fix in there, and it's doing pretty much what was expected and re-intensifying as it came over the southern Gulf. And now the thoughts are that it'll maintain hurricane strength to landfall. So let's see what that latest advisory shows. I haven't seen it yet either, so we'll wing it together on this one. No real change. It's going to make landfall this afternoon, a little faster than what 48 hours is forecast, but almost exactly on the track that's been forecast now for the last 2 days. In southeast Louisiana, south of Homa, then go over the New Orleans area, southern Mississippi, Alabama, and race northeastward. And they've been telegraphing in the advisories that there's going to be a lot of damaging wind gusts as we go further inland. I'll talk a little bit about that as we go further on. Rainfall potential is a lot less than what you would typically see on the Gulf Coast. We don't normally see a hurricane moving 25 miles an hour or quicker coming inland here. So patches of 4 to 6 inches of rain, with a lot of the rain falling well in advance of the center of the storm, and then fast moving, and then more rain up over the Appalachians and into the mid-Atlantic over the next day or two. And so a large area is in the slight risk of flash flooding, but not the really phenomenal flooding like we saw with Sally earlier this year. Jamie can tell us a lot more about the storm surge than I can, but this is what he put out. Fairly significant surge from where the storm makes landfall all the way around to the western portion of the Florida panhandle, with the peak here in the east-facing coastline in southeast Louisiana, and of course the Mississippi and part of the Alabama coast seeing the peak surges. Consequence of that is a storm surge warning. I'll get that up here and zoom it once so everyone can see it. Basically, the areas I just described, from the Pensacola Bay area westward to west of Houma into the Morgan City area. And you can see this is all outside of the hurricane protection levee systems in New Orleans, but there is a lot of low country in there that gets flooded even at the levels that this storm will produce. What else was I going to show here? I think that was it. Okay. The tornado threat is covered by the Storm Prediction Center. The forecast soundings show a tremendous photograph with from the surface into the lower levels, which is typical in the northeast of the landfalling hurricane. And there'll be quite a bit of storm relative helicity value sufficient to support tornadoes in a marginally unstable atmosphere. So don't be surprised if a tornado watch comes out shortly for the landfalling aspect of the hurricane. I promised you I'd talk a little bit about the gusts. I spend a little money and get some of the extra output from the ECMWF, and this shows the peak gusts over a 6-hour period preceding the time of this graphic. And as you can see at landfall, there's a swath there of peak gusts in the greater than 90 knot values showing up in southeast Louisiana, and of course the southern coast of Mississippi, and 70 to 80 mile an hour gusts up in South Alabama, and overnight in the North Georgia and the rest of Alabama and the east part. Strong wind gusts are forecast. This is going to bring down a lot of trees and power outages, and it'll probably surprise people in the Appalachians. It's also forecasting high gusts in the southern Appalachians and the Piedmont as it goes through there. The 850 wind forecasts hold the 100 knot 850 winds with the phasing of the upper system and the hurricane as it moves up into this area. So with that, I will introduce our speakers, and we will move on to today's show. We've been talking there periodically. We talk about some of the aspects of hurricanes and climate change, and we're blessed this weekend or this week to have with us 3 speakers who can address some of these issues. First up will be Dr. Tom Knutson. He's a climate modeler at the U.S. Geophysical Fluid Dynamics Laboratory in NOAA. His research covers hurricane activity, the link between climate change and hurricane incidence and intensity, and climate change detection and attribution. Recently, he's led a project at GFDL aimed at simulating past and future hurricane activity using regional high-resolution models. So with that, Tom, give us your words. Need to unmute. Unmute, Tom. You're still muted, Tom. Nope, still muted. Wonder what's going on with that, Alex.
I'm not sure.
There we go.
Sure. Sorry, I was getting my screen shared. Okay.
All right.
So can you see my screen now?
Yes, sir.
First screen? Okay. Yeah, so I want to talk about the link between climate change and hurricanes. So we know that there's been global warming over the past century, and human emissions of greenhouse gases are responsible for a substantial amount of that warming. But the question is, what has happened with hurricane activity? And if we have continued global warming through the coming century, what will happen to hurricane activity, say, in the Atlantic Basin? Just because we have a big impact on global mean temperature doesn't necessarily mean you're going to have a big impact on hurricanes. So there's a whole science that's been looking at this question of the link between hurricanes and climate change. So I'm going to talk about that today in two parts, really. First, we're going to look at past data to see what's actually showing up in the data itself. And then in the second part, we'll look briefly at models and what models say about the future. But the past data sort of informs how much confidence we can have in the model projections. So if we look at, for the Atlantic Basin, at a number of time series which are relevant to hurricane activity, this panel shows a number of these time series. The top panel is global mean temperature, showing that rise over time. And we also see that tropical Atlantic sea surface temperatures have increased since the 1800s, similar to global mean temperature, but with more multi-decadal variability. Now, the raw number of hurricane counts has also been increasing, sort of like the tropical sea surface temperatures, but we think there's substantial undercount of hurricanes back in this earlier part of the record. So if we adjust for the amount of ship traffic in the Atlantic Basin that was actually trying to detect these early pre-satellite storms, you get basically no real trend over time. And that's consistent with the US landfalling hurricane record, this orange curve here, which shows no real trend over time. So in contrast to global mean temperatures, US landfalling hurricane frequency has not increased significantly since the late 1800s. So that's important to keep in mind. There have been some other types of changes noticed in hurricane activity. A recent paper by Jim Knutson finds that hurricanes, once they get over land, over the continental US, have been slowing down slightly. There's been a 14% slowdown in the median propagation speed since 1900. So storms are moving more slowly, and this could have impact on the amount of rainfall that they're dropping, because as a storm lasts, is spending more time in a certain area is dropping more rain. We don't really know what's causing this slowdown yet. It's not something that's well modeled at all. So it's something we're keeping an eye on. When you look at Atlantic hurricane activities, looking back in time, something that's very prominent is the so-called multi-decadal variability. This shaded curve in the top is major hurricane counts in the Atlantic Basin. And you see that it was high in the 1940s and 50s, then low again in the 60s, 70s, and 80s, and then high again after 1995 or so. So you have these swings between active eras and inactive eras, but no real significant long-term trend in this, in major hurricane counts. Now these swings seem to be related to changes in ocean circulation, as inferred by this blue curve, the AMOC. That is an index of the Atlantic overturning circulation, and also related to changes in vertical wind shear in the main development region over the tropical Atlantic. That's the red curve. All these are related. In the quiet periods, we have more wind shear, and in the active periods have less wind shear. And these multi-decadal changes may be related to natural variability, or also may be partly forced by changes in aerosol forcing over time. And let me show you what I mean there. So first of all, this is a model simulation. This bottom figure is a model simulation of the trend in number of storm counts since 1980. So since 1980, there's been a rise in storm counts in the Atlantic Basin. Now, as I showed earlier, this rise since 1980 is sort of the most recent in one of these sort of multi-decadal changes. So it's not really a long-term trend. But anyway, this rise since 1980 is simulated in this model. Here's model simulation, so it sort of matches up, as well as the rest of the pattern of the change in tropical cyclones since 1980. So this is a new study. So models are able to capture the pattern of a trend. This is work by my colleague Hiro Murakami at GFBL. So it's able to capture this pattern of trend. And now, what about the Atlantic Basin, though? So this is the time series from that model going back to 1920 of tropical storm counts. And the black curve is the observation showing that rise in storm counts since 1980. And the red curve is the model. So you see that in the model from 1980 to about now, there's been a temporary increase in storm counts in the Atlantic, similar but weaker than the observed change. But this is superimposed on a long-term decline. In the model, greenhouse gases cause a long-term decline in tropical storm frequency in the Atlantic. But this little kink in the curve is caused by a reduction in aerosol forcing during this time period. So we had a lot of sort of aerosols and pollution basically coming off North America early in the 20th century. And then with the Clean Air Act in the 1970s, there was a reduction in that aerosol forcing, and we got a temporary sort of warming due to that effect in the tropical Atlantic, which leads to a temporary increase in storm frequency. So we think that many of these changes we're seeing since 1980 in the Atlantic Basin may be more of sort of temporary changes associated with this reduction in aerosol forcing or natural variability. There may also be some greenhouse contribution. We're not sure. So trying to tease out all the different factors there is a very difficult scientific problem. So we have seen in the Atlantic Basin an increase in the proportion of storms that reach major hurricane status. That's this middle plot here. We're also seeing that globally. Again, this is something we're seeing just since 1980. So we don't have records going back to 1900 of hurricane intensities globally. We just don't have good enough data to do that. But beginning in around 1980, we have satellite data that we can depend on for a relatively homogeneous look at intensities. And that's showing an increase since 1980 in the fraction of storms that reach major hurricane status. It's especially pronounced in the North Atlantic, but we also see it globally. We're not sure. This may have some greenhouse warming contribution to it, but that's still sort of work to be settled. It may also have some natural variability contributions. This is relatively recent work out by Jim Knutson at NOAA. Sea level rise is another important angle to remember. The sea level is rising along the U.S. coastlines, and all of the things equal, when you have sea level increasing, you're going to have higher, worse coastal flooding problems, higher storm inundation levels, just due to the sea level rise itself, even if the storminess doesn't change at all. So the background sea level is a major player in storm impacts, and of course that's related to global warming. Anthropogenic forcing is believed to be causing a substantial part of the global mean sea level rise we've seen since 1900. And I think Jamie Rhome will talk more about this later. So in summary, what's the past data showing? If we look at the longest term trends, where we do have some human influence on global temperatures and sea surface temperatures in the tropical Atlantic, global warming is also increasing precipitation extremes. For example, in eastern Texas, there seems to be an increase in precipitation extremes. It's leading to sea level rise along the coastlines. We're also seeing this slowing of propagation speeds over the continental U.S. We're not sure why that's happening yet, though. And as I mentioned earlier, there's no change in U.S. landfalling hurricane frequency since 1900. And if we look at the shorter time period, trends since 1950, I showed those strong multi-decadal variations in major hurricane counts that I showed, again, with no real trend. So there's no real trend apparent in the major hurricane counts, at least in the Atlantic Basin so far. It's only when we look at these trends since 1980, which are relatively short for looking for a greenhouse contribution, that we see a number of trends in the Atlantic: increased intensities, proportion of storms reaching Category 3 intensity, rapid intensification rates are also increasing. They show that in the data. All these are going on in the Atlantic Basin. The issue is that we can't really just blame these directly on greenhouse warming, because there are these other things going on at the same time. The strong multi-decadal fluctuations due to natural variability and partly due to aerosol changes, as I showed earlier. So there's a lot of complicated things going on in the Atlantic Basin, which makes it kind of difficult to actually sort of find the smoking gun for greenhouse warming in terms of the hurricane characteristics themselves, with the exception of the sea surface warming and the sea level rise in particular. And in fact, these recent increases in tropical storm frequency, this recent study shows that might just be a temporary due to this, mainly due to this reduction in aerosols over that time period. So, okay, that's the past. If we look at the future, use these climate models to look at how, if we have continued global warming, say another 2 degrees of global warming, what does that mean for Atlantic hurricane activity? So models suggest that rainfall rates in hurricanes are going to increase by about 7% for every 1 degree Celsius rise in sea surfaces temperature. So that works out to about a 15% increase by late in the 21st century under these sort of standard scenarios, future scenarios. Hurricane intensities are also projected to increase, and the magnitude of that is about 3% by the end of the 21st century. So it's not a huge change, but it's something that we see consistently in the model simulations. Now, in terms of numbers of storms, the models are sort of split. Some of them say increase, some say decrease. We're not really sure what's going to happen to the total number of storms. And same with the number of category 4s and 5s. We think a greater fraction of storms are going to reach category 4 and 5, but we're not really sure about the number of category 4s and 5s in global warming. So increased rainfall rates, some increase of intensity, but we're really uncertain about frequency in the frequency of either tropical storms in general, categories 1 through 5 hurricanes, or category 4 to 5 hurricanes. It's really difficult to say at this point. So in summary, when we're looking at future projections, there's concern about storm surge effects due to the increase in sea level rise, which is going to lead to higher storm inundation levels. Tropical cyclone rainfall rates, we think, are going to go up because the atmosphere is holding more water vapor that's being converged toward these hurricanes. We're projecting about a 3% increase in average tropical cyclone intensities in the Atlantic Basin. We have about medium confidence in this projection because we don't yet have a detectable change yet in the observations. We have about medium confidence that the fraction of storms that reach category 4 and 5 levels is going to increase in the Atlantic Basin. But we're just not sure at all about tropical storm frequency or the frequency, overall frequency of these category 4s and 5s. So that's a quick look at the science, what the science is saying on this question. It's a complicated question. There are a lot of factors that one has to keep in mind. And so that's just a quick overview, and of course, happy to continue discussion on this during the discussion session today. So thank you.
That was an excellent overview of the issue at hand there, Tom. For those viewing, we decided we're going to do the questions at the end and have all 3 speakers speak. So next up is Dr. Brian Haus. He's the chair and professor of the Department of Ocean Sciences at the Rosenthal School of Marine and Atmospheric Science associated with the University of Miami. He studies coastal ocean surface currents for application to oil spill transport prediction and response, radar remote sensing of oceanographic processes from satellites and coastal radars, shelf and inlet dynamics, and wave current interactions. Today, though, he's going to be talking to us about some aspects of rapid intensification that he's been looking at.
Thank you, and thank you for that segue, Tom. I think you touched on a lot of the overlying issues that to motivate the research we're doing. In particular, I'm concerned, I'm kind of approaching this from the opposite scale as the global models, is looking at what happens at the air-sea interface in a hurricane and what that means for forecasting. And in particular, we're interested in the rates of 2 things, really. One is the rate of the heat transfer from the surface, and the other is the frictional drag. And we approach that by doing, I'm a physical oceanographer that does measurements of air-sea interaction processes in the laboratory and the field. And what I'm going to talk about today is laboratory measurements, where we can isolate a lot of the things that, other things that might be happening in the storm, similar to the issue with attribution that was discussed, and try to understand what is happening right in that term, because all these things go into the hurricane models in terms of how you forecast the intensity of the storm is the amount of heat that gets transferred from the surface, and then the amount of drag that the surface might put upon that. So we have a unique tool at the University of Miami. It was built in 2014, and that is the Sustain Laboratory, where we can generate winds up to Category 5 strength in the laboratory, and at a relatively large scale, about 75 feet by 18 feet by 6 feet high. And with that, we can create the conditions like those at the interface between the air and the water in a tropical cyclone, make measurements related to the transfer rates, and hopefully get a better idea of how to put that information into a model. And all of the hurricane forecast models use some type of expression to do this, or pretty much use the same one, and they have these coefficients, whether the heat transfer coefficients and the drag coefficients that are used in these models, and those are based on information, very limited information that we have in the field, and from studies such as this in the laboratory to provide guidance for how to specify those coefficients. So this is, see if I can get the movie going here. This is an example of what it looks like in the lab when we have very high winds blowing over the surface. And you can see some of the things we're particularly interested, which I'm not going to talk too much about today, but one of the real questions is how you treat sea spray into this problem. And so what you see is this incredibly energetic interface. This is about a Category 2 storm here. It's not even the full one. With the full speed on it, you don't really even see much at all going on, meaning that there's so much spray in the air that it's really difficult to get a good view of what's happening. And one of the other things, just as a side note, that we do in the lab is we have a mechanical wave generator so that we can look at things related to, say, when the wave conditions are different in different quadrants of the storm. And as I already alluded to, we're interested in these two terms: how much of the friction of the ocean slows down the storm, and how much the heat transfer from the ocean, we know that powers the storm, and that comes off as sensible heat and as latent heat. And we're trying to measure these key terms. And work that was done previously that I was involved with in 2004 was measured the drag coefficient of the ocean and the heat transfer coefficient in the laboratory. And these terms are widely used in the WRF model and other models that are used operationally right now. Information was derived from our laboratory in Miami. And this is how we use some techniques that'll enable us to measure these terms in the lab. It's very difficult even in the laboratory, as you could see from that picture. It's a very energetic condition. A lot of the sensors that we use to measure things don't work well when they're getting hit by spray and all that, even in a laboratory setting. So it's a challenging measurement to make in the laboratory, and of course that is much more challenging in the field, which is why we're in the laboratory. So we have this set up here, and we've got some unique things, and I won't go into too much detail, but allow us to see the whole development of the wave field as the winds move along. There's these video systems that we've got, and we can measure different things related to the fluxes of heat and momentum across the surface. Now, I'm gonna, this work came out just this year in Geophysical Research Letters. And so the first thing, this is a result of a National Science Foundation study, wherein we said, okay, this was work that was done in our older tank, smaller facility, could only get up to about Cat 2 wind speed. And we said, okay, well, we told NSF, the first thing we're going to do is we're going to recreate what we did in 2004, make sure that we're comparable to that, and then we're going to move to the bigger laboratory and go up to Category 5 winds. Well, that turned out to be more challenging than we had anticipated, because when we went to do the measurements, we discovered that we weren't exactly agreeing with what we had found previously. And through extensive reanalysis of all the data, we've actually discovered that there was a misapplication of one of the ways that we relate the stress in the laboratory to the centerline wind speed. So we actually we had to revise that Donald 2004 value, which was important to get out because it is widely used in the hurricane models. And we see that with this revision, the data that's just shown in the red and the circles here now agrees through is a bit higher than what was previously here. You see the red triangle is the difference between the previously observed values and the current ones, the red to the black. So it shifted up a little bit, but fortunately did not significantly change the level at which it's saturated, which I think was the key, which was the key result from this study in 2004, was that the drag coefficient didn't keep going up, which would have led to a condition where, with the friction increasing basically as a cubic of the wind speed, then you would suppress stronger storms in the model. And our work in 2004 showed it leveled off the drag coefficient, which means a quadratic increase in the friction. But in any case, this data still shows that, just shows it levels off at a slightly higher value, about 10%, and also agrees with all the available field data at lower winds. So that's an important result to get out there, as we have now published this corrected curve for use in the models. And one of the things that we're continuing on working in the larger facility now is to extend this data out to Category 5 winds, which will be the first data available at the air-sea interface in those kinds of wind speeds, first quality data, what's happening right there. And also look at the different quadrants of the storm and how the friction might change when you go through different types of wave conditions. In the forward right quadrant, you have the wind and the waves moving in the same direction. In the rear quadrant, you have a lot of rear left quadrant, you have a lot of crossing seas and things like that. So there's a lot of different quadrant variability that has been observed in the field. And we're going to be exploring what the actual wave conditions themselves, what they have on effect they have on the drag coefficient. Early indications are it's significant. So and just a real quick little explanation, a little bit more about what we do. One of the things, in addition to this kind of fundamental look at the forcing that drives the rapid intensification process, we're also interested in impacts. And I'll show one quick more little thing here, looking at studies and how you build in these kind of conditions. So that is looking at this really high winds, what the loads are on different types of structures, and how we might design those things better. And additionally, how we might design our coastlines using things like our hybrid artificial reefs to protect the coast. So I will stop sharing now, and we'll go back to the next presenter, I think, and look forward to discussing some of these issues later. Thank you.
You're muted, Bill.
Bill forgot to unmute. That's been a while since I've done that. Okay, I'm back in business. That was fascinating, Brian. I've spent a good chunk of my career getting heartburn over not being able to forecast rapid intensification. So any work that gets us closer to that goal is going to be fabulous to see. Our third speaker up today, good friend of mine I've known since 2007, actually, is Mr. Jamie Rhome, who is everything storm surge when it comes to operational forecasts and warnings. He came to the National Hurricane Center back in 1999 after he finished his degrees at NC State. And he's been in charge of the nation's storm surge program at NOAA since 2008, and done a gangbuster job of taking us from a two-line text product advisory to a excellent forecast and warning and display system that we currently have in place. And his efforts have gone noticed. He's been recognized numerous times, most recently with the 2019 Service to America Medal. So Jamie, tell us what you got today.
Hey, Bill, just want to make sure we can hear okay, got good audio?
Perfect.
And I was looking through photos of past hurricanes last night, so I was being a little bit nostalgic to when you and I worked together previously when you're at the Hurricane Center. I don't have a presentation this morning, and I wish I had a good excuse. Unfortunately, it's due to the fact that I'm very much involved in operations with the current Hurricane Zeta. I bounced right off the forecast process to come over here literally like a couple seconds apart. But I can build upon the themes that Tom touched upon briefly, and then we can have a little bit more time for open Q&A, which is probably what everyone's most interested in. The natural thought process when you're talking about hurricanes in a warming climate is people tend to focus and gravitate to this notion of more hurricanes or stronger hurricanes. And I think the bigger story here is water, both increased storm surge risk owing to sea level rise and increased rainfall risk owing to the climate, a warming climate able to hold more moisture and rain. And often that heavy rain comes hand in hand with the surge. And so you don't need me to tell you that if it rains a lot in a hurricane, gravity prevails, the water flows into the river, and then the river tries to flow into the ocean. But if you've got storm surge pushing up into that river estuary system, those two collide and they do not make very good partners. In fact, that collision of the freshwater discharge trying to get into the ocean and the ocean trying to move up the river causes some of the worst flooding, at least from hurricanes and tropical cyclones, the worst flooding situation that we know. So if it's raining more, or at least the potential to rain more in hurricanes, and sea level rise is causing more storm surge, then those two are magnified. And now it gets a little bit even more complicated in that, and I'm going to focus in on sea level rise and storm surge, which is sort of my area of more coastal modeling. A lot of people make the mistake of saying, okay, in a future climate, if there's 1 foot of sea level rise, you just add that 1 foot to future storm surge. But the way storm surge and sea level rise work together is what's called nonlinear. The same is true with tide and storm surge, is you don't just add them up. The way they interact is incredibly nonlinear. So for example, if we took a storm that produced a 5-foot storm surge today, and then in the future with a 1 foot sea level rise, you can't just say 5 + 1 = 6 feet of storm surge in the future. It's some of our sensitivity studies that we've done in-house. The worst one that I've seen is a 1 foot sea level rise because of the nonlinear component of how it interacts with storm surge resulted in 5 feet more storm surge than if you took that 1 foot away. So it's not as simple as, hey, 1 foot doesn't sound like a lot. Doesn't sound very impressive. But when you take into account the nonlinear component of the interaction with storm surge, future hurricanes, regardless of whether they're more frequent and regardless of whether or not they're stronger, future hurricanes will have a greater societal impact in the form of flooding potential. And owing to the way this nation approaches flood risk and flood insurance, it's going to be a nasty collision course in the next few decades. So few people buy flood insurance in this country, unless you're required, if you have a mortgage and get a loan from a bank and you're within the 100-year flood zone, you're not required to have flood insurance. And few people realize their flood risk. And unfortunately, if they get hit by a 105-year storm or 150-year storm or 200-year storm or 300-year storm, and their house is flooded and they're not carrying flood insurance, then the regular homeowner's insurance policy is not going to cover that, which can be financially disastrous for most people who couldn't sustain that type of a hit. So I'll stop there to leave plenty of room for questions and answers and interaction amongst everybody on the panel. Thank you so much for having me, Alex and Bill and Tim.
Awesome. I think I'll start off with you, Jamie, with a question I had that in case you get pulled away on the storm and all. That's first I'd really thought about the nonlinear aspect on the surge there. Have you done a lot of studies on the coastline of that, or to identify where this might be? Because that'd be a very useful tool for local officials in trying to convince people that they need to start doing things now in anticipation of the sea level rise.
We happened upon that kind of accidentally because, the HurricaneCenter's mission is not, sea level rise, climate change. We happened upon it via the so-called slosh moms and meows, which are risk-based products that aren't intended to look at sea level rise. They're just looking at the risk of hurricanes. And we were looking at it from the effect of, given how frequently we update them, which is generally every 5 to 10 years, how perishable is that product in a rising, sea level? What sort of sea level rise do you need to happen before that product loses its value? It perishes, becomes perishable. And so we basically asked experts within NOAA to give us different sea level rise scenarios. And then we went back and recomputed all the slosh moms, which again is just a risk product, with these different sea level rise scenarios. And obviously, you're not, if you're looking at decades, and you're looking at, inches and a foot. So we ran several with a 1 foot rise and then compared those moms to the non-sea level rise moms. And the differences were not at all intuitive. And, you would think, oh, I'll just add a foot to everything and it'll be fine. In some cases, the flood went down, which was not what any of us, I think, would have expected. The cases were rarer than the flood potential going up, but that was sort of surprising. And then in some cases, it went up substantially more than the initial offset in the modeling due to the sea level rise. So that's where we discovered that, and it makes sense. I mean, the way surge interacts with tide, which is far more modeled and studied, is highly nonlinear. So we'd expect a similar result with sea level rise.
Interesting. Yeah, it'll be interesting to see follow-ons to that in the future. Question I had for Brian. How well are we able to input your findings on air-sea interaction in a hurricane model such as the HWRF?
Well, back when we did the original study in 2004, our assumption at that time was that we would be able to kind of get some idea of trends and some kind of physical understanding of the processes, but that the actual direct values would not be something that you could plug from the lab and plug into the field. As it's turned out, the values that we obtained have been pretty much supported by available dropson data and other measurements from other sources in the field. So because we can cover a good range of data with a pretty low variability curve, the actual values from the experiment have been widely used in the forecast models, which was not our anticipation because of the different scales, particularly in the momentum transfer. And that's because waves, there's multiple scales involved when you look at surface waves and things like that. So going forward, we're exploring this. And again, there's always that caveat that you need to do measurements in the field to be able to look at the full range of physical scales. But so far, what we have found is compared very well directly with the measurements in the field. For heat transfer, our rates are pretty good because those are molecular scale processes. They're not really controlled by the waves at all. It's about what's happening right at the interface where that heat is coming off. But with the drag and the friction, you have the wavelength scales of the large waves and things like that, that may also exert some significant influence. We're looking at that with the study of the wave effects.
Very interesting. Tom, on the detectability thing, some of these small like changes, when will, I mean, I see people mainly in media, so it's not substantiated by research, stating that this shows that hurricanes are getting stronger. Or I've actually had a couple of studies and a thing I'm looking at on rainfall here in Texas that give a % of increase in rainfall on Hurricane Harvey due to climate change. And I read them and I find I tend to be kind of skeptical. I don't know whether we've had enough climate change to really be able to say that sort of thing. What do you think?
Well, let's take Hurricane Harvey, for example. The primary driver of this huge multi-day rainfall event was the stalling of the storm in the Houston area. So what we're saying is that, okay, we're not really sure if global warming is going to cause hurricanes to stall out more in the Houston area. We're just not sure. I mean, some of Jim Cawson's work showing a 100-year reduction in average storm propagation speed may be relevant to storms like Harvey, because he's saying that storms may be slowing down systematically. But what climate science can already show is that extreme precipitation in general around the globe in a majority of regions where we have enough data to analyze it, extreme precipitation is going up. And that's precipitation from all sorts of causes, not just hurricanes. What we don't yet have is a detectable signal in hurricane precipitation per se. We just have it for precipitation from all sources. We already see that's going up, and that has been linked to anthropogenic forcing in part. So again, I think when does the detectable signal emerge for hurricanes? I think it will probably emerge pretty soon for the hurricane precipitation signal, because it's already emerged for extreme precipitation in general, because we have more data, of course, in that case. But what about the things like the intensity? That's trickier. I showed that new study by Knutson with finding the fraction of storms that go over that category 3 level has been increasing. That was since 1979. Not just in the Atlantic, it's increasing in the Atlantic, but it's also increasing globally. Okay, so there's a possibility that we're seeing some emerging greenhouse-related signal in that case, because we see that signal in the full global data. However, we don't yet have a clear, what we call a formal detection attribution study on that particular change. We have this very significant looking trend in the data, but we're not yet sure what the relative contributions are of greenhouse warming versus natural variability, because it's over a relatively short period from about 1980 to now, so about approaching 40 years. We like to have something more like 100 years of data to find these detectable signals and demonstrate that they're different from natural variability. So in the case of global temperature, we have a very strong signal. It's well established that it's unusual compared to what we think natural variability can do. We just don't have that strong a signal to noise ratio yet for these hurricane related signals. But we do have some interesting signals showing up in the data since 1980, and this global increase in the fraction of storms reaching category 3 or higher is one of them. But we're still sort of in the thick of it with the science, trying to sort out what are the relative contributions to those changes. So it's an interesting question, and we just have to be a little bit more careful, I think, when we start blaming aspects of hurricane activity on human-induced climate change, just because the signal to noise is not as strong as it is for things like global mean temperature or even sea level rise. So we have to be a little careful in what we say. That's not to say that the greenhouse warming is not having any effect at all. There may be some effect there. It may be starting to emerge. We're just saying that we can't make as confident a link of these changes of intensity and so forth to greenhouse warming as we can for something like global mean temperature. That's just what the state of the science is.
Right. Can I make a comment here? I totally agree with your assessment of the global trends. I just want to comment that we should also remember that regionally, there's a lot of even sub-basin scale differences in heat content in the water that are potentially climate driven. There's, there may be more, the North Atlantic, the Caribbean was very warm this year. Things like that are not global signals that you may not be able to attribute globally to climate change, but there's regional variability in sea level rise. So particular areas like the Northern Gulf Coast may be much more susceptible to storms because of that. And, the attribution to the global climate signal is a question, but to say that there's a lot of warm water there and, is a more direct interpretation. And whether you say that warm water is there because of climate, we don't exactly know all the things that are driving that. But I think that's an important distinction, that there are a lot of regional effects, the North Atlantic, as you go up farther up the East Coast, where here we are in, almost November, and we have, still relatively warm water in the Gulf and stuff.
Yeah. The question for you, Brian, that came up here. Do you have any thoughts on the increasing frequency of rapid intensification with respect to the warming in the ocean?
Well, the intensification is, driven by sort of the absence of factors that impede it, like wind shear and dry air being entrained and all that. So there's a lot of things that can, put the brakes on it. But the fundamental thing that needs to be there is the presence of warm ocean water, and particularly if the storms are moving slower, warm, deep ocean water, to deeper levels, the overall heat content. So that's a prerequisite for rapid intensification. And I think that, as you get more warm water out there, at least that prerequisite is established, right? If you have the warm water and you don't have the dry air and you don't have the wind shear, you don't have all these other things that might impede development, then that's one aspect of it, for sure.
Could I make a comment on the rapid intensification issue?
Yep, go ahead.
Yeah, so I was co-author on a paper out recently by Batia et al. In Nature Communications, which looked at rapid intensification and rates of rapid intensification, particularly in the Atlantic Basin. And we did find there's been an increase since 1980 in the proportion of storms that undergo rapid intensification in the Atlantic Basin. So rapid intensification, the rates are increasing, and the fraction of storms undergoing rapid intensification has increased since 1980. Now the question, so that's clear, it's a clear signal in the data. Now the question is why? What are the relative contributions of natural variability versus greenhouse warming to that? Because we do have, as I showed, this multi-decadal variability going on in the Atlantic Basin, which is apparently not so strongly linked to greenhouse forcing. But you could still have greenhouse forcing and greenhouse warming going on and contributing as well to this recent rapid intensification. Really, the challenge for us is trying to sort out these relative contributions. We're not saying that global warming is not contributing or causing some of this observed increase in rapid intensification. It very well may be. What we're saying is that in the Atlantic Basin, it's a very difficult basin to find the signal in the noise because there's so much natural variability, there's so much multi-decadal variability going on in the Atlantic Basin, whether it be from natural variability or from changes in aerosol forcing, whatever is causing it, it does make it very difficult to tease out these long-term trends that we expect are in the data related to greenhouse warming. We do expect based on models, that we should already be seeing some increase of intensity in the Atlantic Basin and probably some increase of rapid intensification rates due to greenhouse warming. But that's a model-based result. It's not something that we can actually see kind of sticking out of the noise yet in the data, partly because our records on this only go back to 1980. Why do they only go back to 1980? It's because we're sort of dependent. We want to dependent on satellite based data to have a more kind of homogeneous look at intensity over time. So we don't really trust these really long records of intensity out over the basin in general prior to these clean satellite records that Jim Cosson has put together, for example. So it's a tricky problem. There may be some greenhouse contributions going on to intensity and rapid intensification and so forth, but it's going on at the same time we have a strong natural variability, strong multi-decadal variability in the Atlantic, which makes it a challenge to actually make confident statements about saying, well, this X amount is due to greenhouse warming and Y amount is due to natural variability.
Great. Tim, what do you got for us?
A lot of comments coming in. We appreciate everybody who's watching today, and I feel like just a fly on the wall watching a great discussion today, and I appreciate you guys for all you're talking about. Our friend Barry has made a number of comments today, and he talks about, going back to what Jamie said, he said your discussion is exactly why he doesn't use the 100-year flood phrase to describe potential flood risk. He said it's a probability that accumulates over time, and it goes a lot farther inland as well. That was his comment on that. I don't know if you want to respond to that at all. I think he's just agreeing with what you're saying. But Jamie, I don't know if you've got any comment on that.
Yeah, I mean, I think the 100-year flood is something we've got to think about as a nation, of whether or not we want to continue to base our understanding and communication to the public of their flood risk on this particular tool.
He also commented that the 2016 Louisiana non-tropical event appeared to be one case with some percentage related to anthropogenic global warming. When it wasn't even a hurricane, it was a non-tropical event that brought tremendous flooding there. So thanks to Barry for the good comments there. There's a couple of others there as well. We appreciate that. No, I think that this discussion today shows that while we've been studying climate change for a long time, we're really in the infancy of this science, it seems like, and we've got so much to learn and so many more years to go as we learn about this. But I think the significant impacts we're already seeing, and it's going to be interesting to see how it plays out. Gentlemen, thank you. Do you have any parting comments? We're coming up on 11 o'clock. We'll go in the order we presented. Tom, do you have anything you want to wrap with? Anything you want to leave us with today?
Well, there's clearly anthropogenic influence on global mean temperatures and even extreme precipitation events and changes in sea ice and changes in sea level. So we have a lot of things where we can really make a strong case that humans are already affecting it and are going to lead to even greater changes going forward. So there are a lot of changes already underway in the climate system that we have to be concerned about, including heat stress. Today, we just focused on one particular aspect, hurricanes, which is more difficult to make that link, just because it's a more complicated process with more moving parts, more things involved. It doesn't mean there's not a human influence. So as a climate scientist, I sort of have to look at the whole playing field. There are clearly many metrics where humans are already having a detectable influence. Hurricanes is a more difficult one to pin that influence on, with the exception of some things like Jamie's mentioning with the sea level rise and the increase in atmospheric moisture, which we think is leading and contributing to this increased precipitation rate. So stay tuned. The science is still active in this area. We're going to continue to study this, and we look forward to new data as it comes in that challenges our models. We're always trying to reconcile our models with observations and increase our understanding of what's actually going on in the climate system. So stay tuned because the science is still progressing on this one.
Thank you, Tom. Brian, any final thoughts, parting thoughts?
Well, I just thank you for having me on the show, and it was a real pleasure and great to hear about some of the other talks. I guess I would just emphasize that there's a lot of things we know and a lot of things we need to learn more about. In particular, the impacts at landfall of hurricanes as they're interacting with the coastline, to the questions about the sea level rise and storm surge interaction. There's a lot of things related to the wind fields and the wind wave conditions as a hurricane makes landfall. So there's a lot of exciting and research to come. I'd say there's a lot of unknowns, but we're making progress. Thank you.
Thanks, Brian. We appreciate it. Jamie?
Yeah, I think this debate, this forum has showcased what really is the state of the science. There's a lot of things that science knows, some things that science doesn't know. The way that tends to get conflated for good storytelling is right, wrong, good, bad, right? And that's where we're missing an opportunity. The science community is missing an opportunity to move policy in society, because all anybody hears down the street is a bunch of scientists can't agree. They're just all arguing. And I know, because I'm out there in the field working with real world practitioners, emergency managers, local politicians. So what we need to do as a science community is, while the parts that are still unresolved are being resolved, let's focus on what we know. And what we know is that the ocean is rising, and it's going to continue to rise over the duration of our lifetimes. And that is going to make coastal communities more vulnerable. And we should get on with making the policy and society decisions and changes necessary to mitigate and protect coastal communities from that evolving trend.
Great thoughts, great wrap up. And Bill, what's your takeaway today? This has been great, a lot of great information. What do you take from this?
Yeah, I resonate with all three of our speakers on where we go from here aspects of it. The fact that we need to constantly convince people that while we don't know everything, there are a few things that are well known now, and here are the things we're working on to improve our knowledge in the future. So, gentlemen, thanks so much for spending some of your valuable time with us.
Appreciate it, guys. One thing I feel good about is that I'm up on the 5th floor at least. So as things rise, at least I'm high enough here at South Padre Island. Guys, thank you. We really appreciate it. Fascinating conversation today. It's been fun to just sit back and listen. So thank you for all of your input today. We want to thank all of our sponsors. We want to thank Plylocks for being part of the program today. Again, they've had a very busy season, and we appreciate them cranking out those Plylocks so folks can stay safe during the storm. USAA, a sponsor of all the events we do with the Storm Science Network. We appreciate USAA. From the South Padre Island Convention and Visitors Bureau, the sun is trying to come out right now. Hopefully we'll end with a sunny day here on South Padre in the tropics. I can take the jacket off before the day's over with. So, gentlemen, thank you. We appreciate it. Alex, what's coming up?
Well, we've got some interesting things coming up definitely for next time around. We are going to be doing a program that is called How Hurricanes Changed History. We've got Dr. Chris Lancy, Dr. Philip Klotzbeck, Dr. Kerry Mock, and also Eric J. Dolan. He'll be out there as well giving us an idea of his information. He wrote a book, 500 years of hurricane history. Again, thank you very much, Dr. Brian Haus, Dr. Tom Knutson, and Jamie Rhome. Thank you so much for being here today. We really appreciate you joining us. And don't forget, folks, join us next week for our next program.
My pleasure.
All right, we're in the oral close.